So I am very grateful for being invited here and having the occasion to give a talk here. And subject of my talk is some appearances of large cardinals in category theory, but some kind of overview of that. But I have to tell you that it will be very personal, because of course I'm not going to survey all things of that kind, but only those which somewhat were related to my interests. And this part of category theory in some sense can be also identified with kind of abstract model theory. So mostly categories I will be talking about will be categories or subcategories of category structures. So sigma is a signature, so it's a set of symbols which could be many-sorted and infinitary, but if you don't like those many-sorted and infinitary, so simply nothing happens if you take them as usual signature, so single-sorted finitary symbols. And of course that's a set of those symbols. So in some sense those categories of structures are categories of structures given by a set of data, by a set of first-order data. Morphisms in this category are homomorphisms, so those mappings which preserve operations and relations. Mostly I will talk about full subcategories. So subcategory is full if you have two objects in your subcategory, so any homomorphism between them belongs to your subcategory. And any subcategory, not only full, but any subcategory is concrete. It means that it can be equipped with a faithful functor into sets. Faithful means that two distinct morphisms go to two distinct morphisms within the same object. So of course this functors goes out of the underlying set functor from structures. So any subcategory of structures is concrete. And on the other hand, in fact, any concrete category can be somewhat encoded as a subcategory of structures, because, for instance, take groups. So of course you can have two groups with the same underlying set, but if you make these underlying sets distinct, so you get a subcategory in fact, because the only additional condition is that distinct objects go to distinct objects. If you want, you can encode it in that way. But such subcategories, so in fact any concrete category is subcategory of sets, but this is quite weird, and we would like to have nicer subcategories than those. And one of possibilities is that one takes full subcategories, of course, but even it suffices to have isofull subcategories. I will come to them later at the end. So isofull means that any isomorphism between objects in your subcategory is a morphism of your subcategory. This is of course not satisfied by this crazy coding, because if you have mapping between underlying sets of groups, so it's not group homomorphism, so it's not isofull, and the mapping is bijection. And one would like to know, in fact, which categories can appear as full subcategory of structures. And the answer is this result of so-called Prague school, Hedderlin, Pulter, Trnkova, that assuming non-existence of a proper class of measurable cardinals, this is quite decent axiom which tells you that there are not too many measurable cardinals. For instance, there are none. So having that, so then any concrete category, in fact, can be fully embedded to structures. You see, it's a little bit strange, because this is a good axiom, because it doesn't enforce you have too many big cardinals. But on the other hand, the result is bad, because this gives some very strange coding of things that, for instance, take topological spaces. Topological spaces can be understood as first-order structures if you take operation, if your relation symbols are indexed by ultrafilters, and the relation is that the point converges to the ultrafilter. But you have a proper class of symbols because you have a proper class of ultrafilters. So topological spaces can be understood as something which is first order, but the signature is too big. You have a proper class of data. So just it's strange to represent them by our structures. It needs a set of data. But it's possible under this axiom. So there's one extreme, that any concrete category can be full limiting structures. Of course, there are categories which are not concrete. The first example of that is due to Peter Fright. What I wrote here, sorry, that's I know one misprint in my slides, but I found the second one. So Peter is not so old. But he proved, so of course it should be 1970, so he proved that this category is not concrete, which is not so easy to do that, yes. And it's typical that this homotopy category is a quotient of a concrete category. It's a quotient of topological spaces. And that's a theorem of Kucherov, which is of that time, that any category is a quotient of a concrete category. So in some sense, any category is quotient of a concrete category, but mostly it will vary with concrete categories. So on the other hand, there are some conditions which somewhat ensure you that a category can be full limited structures. And this is here. So it's a little bit technical for those who were not exposed to category theory. So bounded means that you have a small subcategory, a set of objects, so that any other object can be glued out of those objects, in fact, the canonical way. It's a kind of density, so also these subcategories are called dense. And the canonical means that you take objects in your category K, and now you take all objects in your small subcategory and all morphisms from these objects to K, and you assume that this is Colmy diagram, so in fact that this K is just glued out of that. For instance, finite sets are dense in sets. Any set can be glued in a natural way from finite sets, that's a typical example. Or any group can be glued out of finitely presentable groups. So these are examples of those dense subcategories.
So small just means set size?
Yes, small it means set sized, yes. So in general, category could be class sized, and small it is set sized. So only a set of morphisms, in fact, yes, not only objects, also morphisms. And this is, and probably all this story goes back to John Isbell. He proved in 1960 that is equivalent to the fact that is canonical functor. So it's explained how this canonical functor works. So you take an object K in your category K, and for A in A, maybe I can write it here. So this E AK is the set of all morphisms from A to K. And since these A's are in the first place, so it's contravariant, so in fact you get a functor from K to the functor category from the dual of A to sets. And density is equivalent to the fact that this functor is full and faithful. So in fact it's equivalent to that K can be fully embedded to presheaves on A, and since these presheaves can be viewed as many sorted unary algebras, and that's another explanation how this functor E works, because imagine that objects of A are sorts. So now you take K, and what's the underlying set of the sort A? Is the set of all morphisms from A to K. And morphisms of A are unary operations, because having a morphism from A to B, then you get a morphism going the other way. Just taking to a morphism to take its precomposition with that one. So this is the way how it is density you can encode your categories, the category structures. So this is what I mentioned. The topological spaces is it's not bounded. One can prove that you don't have a small dense subcategory here. The dual of sets, which is in fact equivalent to the category of complete atomic Boolean algebras, is concrete, but it's bounded if and only if this axiom M holds. So this axiom M is in fact responsible for the fact that somewhat set op has more than subcategory. Again, it goes back to Isbell. And I have to say that this Prague school somewhat was inspired by Isbell, so this story really started with him. So now examples of categories which are not bounded. So take ordinals and take it as a ordered class, which means this is a category. So ordinals are objects, and morphism means that is less or equal than. Yes, so if I just take morphism between ordinals, it's the same thing as alpha is small or equal to beta. So I can just, and this category is concrete. And it's not bounded because you cannot create something from a small thing. You cannot get all ordinals here. And the same is with dual of ordinals. And the same with large discrete category. So what's a large discrete category? So it's a category which is a proper class of objects, but only morphisms are identities. So this is just proper class of objects, so, but only morphisms are identities. So it's a large anti-chain as an ordered set. So these are categories which are not bounded, and now Vopienka's principle in fact says that this large discrete category cannot be fully embedded to structures. You see, because under this M, anything also large discrete category can be in fully embedded to structures, which is very weird because you can make a proper class of total independent things which is a set of data. And Vopienka, this is theoretical, this statement. In fact, this is just Vopienka's principle. And it's equivalent to the same thing with ordinals. And Vopienka's principle states that dual of ordinals cannot be fully embedded to structures. So one does not know, one has this thing, yes? Why it implies the negation of M, because under M anything can be fully embedded to structures. So if, and just Vopienka or Vopienka prohibits something. So so both imply that's a proper class of measurable cardinals. And that's easy to show that Vopienka implies weak Vopienka, because if you negate weak Vopienka, so you have some large chain going down, so which means that it should consist of surjections, essentially. And you can kill surjection by adding new relation non-equal. So it's easy whenever you fully embed dual ordinals that you fully embed large discrete thing. So these are some kind of easy implication. Of course, this implication about negation of F depends on this quite difficult result which I mentioned of the Prague school. But this is a really frustrating problem. Nothing is known about the position of the Vopienka's principle among those two. It could be even equivalent to one of those. Nothing is known about that, and any attempts to do that failed. So here, but one knows that Vopienka's principle is stronger than the existence of proper class of measurable cardinals, because it implies the existence of proper class of much stronger cardinals than measurable, for instance, extendable cardinals. So Vopienka's principle is stronger than negation of M. And now we came to this question in some sense with Adam and Trnkova, and the first thing is that Vopienka's principle is equivalent to the fact that any full subcategory of structure is bounded. You see, because Vopienka's principle in some sense is bad because it's very, very high cardinals, but on the other hand, it's good because only those categories which should be fully embedded are fully embedded. Only those which have this trivial condition that they are bounded, so no other category can be fully embedded under Vopienka's principle. So this large axiom makes life much smoother, that you can fully embed structures only those which can be embedded trivially. So to show you how weak Vopienka's principle appeared, So I need the definition of a reflective subcategory. So definition is written here, but maybe it's better to give examples again for those who never met this concept. For instance, abelian groups are reflective in groups, and the reflection, this M star, is aberramization of a group. Or compact Hausdorff spaces are reflective in topological spaces, and this star again is a check-stone compactification. So this is a very frequent situation. And the first property of reflective subcategories is that they are closed under limits. Well, again, limits, this is category construct. For instance, take product. So Tikhonov's theorem tells you that compact spaces are closed under products. So this is a special case of that. And also it's closed under equalizers, which there means that they are closed subspaces. Closed subspace of compact is compact, Hausdorff. So they are closed under limits. And you can ask now, if something is closed under limits, is it reflective? And that's equivalent to Bopinka's principle. If you do it in structures, so always under full circle structure, I mean what I explained before, so structures of sigma. So you see, because this reflectivity, say one can say it's a combination of two things. It's closed under limits, this is something which can be checked easily, and some smallness condition, which just gives you this reflection. This is called solution set condition. And the smallness condition somewhat goes free out of the Bopinka's principle. And in fact, it's equivalent to that. So this is how the Bopinka's principle somewhat appeared in, how to say, in reality. It's interesting that you can take dual concept. So if you just revert arrows, so instead of reflective, you have co-reflective. So again, it's a theoretical, but now it corresponds to Bopinka's principle. So now I need some more category theory, but not much. So the first thing is, what does it mean that an object is lambda presentable? So lambda is a regular cardinal, and one takes an object and one takes its home functor This is something I used in fact, but this is now covariance. Which sends to an object X the set of all morphism from K to X. And lambda presentable means that this functor preserves lambda directed colimits. So colimit that's due to limit, and lambda directed means that it's indexed by lambda directed posets. Maybe I give you some intuition about that, again for those who somewhat well exposed to these things. That's a very typical use. So if you have an ascending chain of sets and you take its union, and if you take some finite subset in the union, so this is a subset of something on the way. This is the usual thing one uses quite often. If it's finite and you have an ascending chain, so finite subset of union is a subset of member of that chain, which in fact means something of that kind, that finite sets are finitely presentable in sets. But instead of chains, you take something which is directed. Directed is a poset that any two elements have an upper bound. And lambda directed means that any less than lambda objects elements have an upper bound. And it goes to lambda presentable. So for instance, finitely presentable groups coincide with finitely presentable groups in a classical sense. It means something which is given by less than lambda generated in less lambda relations. So this is somewhat a categorical way how to assign sizes to objects, so presentability ranks, just from the category itself, no underlying sets at all. lambda pre-accessible category is a category which this will be somewhat stronger than bounded. So it did have again a set of objects, but those objects are now lambda presentable, and any object of K is lambda colimit of those. So now it's somewhat much nicer than before that it's a colimit of those. It should be lambda presentable, and it's a lambda colimit of those. For instance, again, finite sets have played a role in sets because any set is a directed union of finite subsets. So that's lambda pre-accessible. And pre-accessible means that there's some lambda, so this is lambda pre-accessible. And as I mentioned, this is stronger than bounded. You take this A as small than subcategory, it's just an easy category theory to show that it's dense then. And moreover, this canonical embedding, that's my second misprint I know about. It should be here set to A op. So A is missing here. Yes, this E goes from K to set to A op. Moreover, it preserves undirected colimits. And lambda accessible is lambda pre-accessible, so this is a smallness condition, but some completeness condition that this category has lambda colimits. So these, of course, accessible means lambda pre-accessible for some lambda. These categories were, their theory was created by Mackay and Tare in '94, and they appear in many areas, and some of these appearances will be presented in a moment. So these are some category definitions I need. So another smallness condition which will be more model theoretical. So just this my notation for the unlike set functor, and downward Leibniz-Kollm-Tarski property, this coming from Leibniz-Kollm theorem downward. So it means that the cerebral cardinal lambda, such as having an objective of category K and a subset of its underlying set, subset of the cardinal is smaller than lambda, so then you can find substructure of the given structure K, L, which contains the set, and this still has cardinality smaller than lambda. Yes, so any lambda small set is contained in a lambda small substructure. And under Wappenka's principle, any full subcategory of structure is not only bounded, but in fact it's pre-accessible, and even it has the downward Leibniz-Kollm-Tarski property. This is quite surprising maybe, because just from set theory, anything which is fully limited structures have such lambda rigid works, but of course you don't know which lambda because just it's given by this axiom. And I learned it from Magidor that this is related to unpublished theorem of Stavi, and one can read it in paper from Magidor and Banan, and that in fact this is the same thing. And corollary again on Wappenka's principle, any full subcategory of structures which is closed under the colimits is accessible, because you get the smallest condition for free just from set theory. Another equivalence with Wappenka's principle, so again, you take full subcategory of structures. So it can happen that you have some lambda colimits in your subcategory which are not calculated like in the whole category, which are somewhat wild. It can happen. But under Wappenka's principle, that's always some lambda say it doesn't happen. So those which exist I don't claim that exist all in K, but those which exist are calculated like in structures. So you see now, this is what I somewhat mentioned at the beginning. You see that some very natural questions which were open in category theory or in some kind of, one can say, abstract model theory, somewhat can be answered or can turn out to be equivalent to Wapinka's principle. Yes, when we presented it for the first time at category theory conference, so one of the reactions was, yes, but those questions which depend on set theory are bad questions. This is just a proof that this question is bad, but on the other hand, you don't know in advance whether it's good or bad. For instance, Whitehead problem, that was the most famous use of set theory by Shellac. So, but I think now people wouldn't tell that, yes. And now I show you, in fact, this a proof, in fact, about this consequence of previous things, that as we Wapinka's principle, any full subcategory of structures which is closed at the limits is accessible. So how one does it? So it's closed at the limits, so it's reflective. So this is what I mentioned. And the reflective subcategory in structures is co-complete, has all co-limits. This is a little bit of category theory. So it has one-weighted co-limits. But those one-weighted co-limits should be calculated like in structures. So it's closed and one-weighted co-limit structure. So following the previous thing, it by corollary 1 is accessible. Here I would like to mention that this large cardinal hypothesis, like Wapinka's principle, can be weakened if the category K, this case always this subcategory, has a lower complexity in Levy hierarchy. That is in joint paper with Joan Bagaria, Kaleska, Seguber, Pedri, Matthias, and me. And as example of that, if this category is sigma 1 in Levy hierarchy, so that's always true. I took the claim that closed limits is reflective. So that's always true. You don't need any set theory for that. If sigma 2, that it's true if there is a proper class of supercompact cardinals. But that's only one implication. I don't say that it's equivalent. Just if it's sigma 2 and there's a proper super cardinal, so this is true that this case is reflective. And if sigma 3, then the property extendable cardinals makes that. Which is somewhat quite interesting, because if you look at some concrete problem of some concrete category, so you can just try to estimate this complexity in the hierarchy, and then you can, maybe you don't need the full strength of Wapinka's principle to do this. You need something which is weaker. And the same weakening is valid also in the other things. So another fact, so accessible functor. So accessible functor is between accessible categories, and to be accessible means that it preserves lambda equality for some lambda. Yes, so these are morphisms of accessible categories. So these are functors which preserves lambda equality for some lambda. One can always, I don't want to go into details, but one can always somewhat to uniformize things and to find one lambda such that both categories lambda accessible and the functor has lambda equivalents. So one can make it with given lambda. But we don't need that, yes. And now take such functor and take full subcategory of the codomain category, which consists of savages of images of this functor. And this subcategory is called powerful image. So the image of F is just the image of F. So the powerful image is the image closed under subobjects. Well, maybe a motivating example for this is that you take functor of three abelian groups. So its image this is accessible functor. It preserves, in fact, all collimates because it's left adjoint. So its image consists of free abelian groups. But in this case, it's also a powerful image because any subgroup of a free group is free. So it's in fact not only image but powerful image. And this is a well-known question. Well, so category saying whether the category of free abelian groups is accessible. But maybe more theoretically, it's the question of almost free groups. So whether almost free is free. And that's known that if there's a compact cardinal, then it's true. So if there's a compact cardinal, then any almost, so this category is accessible. On the other hand, under constructibility, this is not true. So this is a theoretical this statement. And Mackay-Paré somewhat generalized that. That assuming that you have enough, it means proper class of some cardinals. So then any powerful image of an accessible functor is accessible. So in some sense, it's a generalization of this fact that having one strongly cardinal, then free abelian groups are accessible. So now, having any such situation, we always need a strongly cardinal which is large enough. So you have to assume that there's a proper class of them. So having a proper class of them, then any proper image is accessible. And recently with Andrew Brooke-Taylor, we weakened the assumption in both ways, in two ways. In one way is that we don't need proper class of strongly compact, but of almost strongly compact cardinals. And on the other hand, we don't need to be closed under subobject this image, but only under lambda pure subobjects. Yes, maybe I should mention something because I will, at the end of my talk, I will come to that, because quite often, if you look at this Mackay-Paré book, so very often they use elementary beddings in proving many, many things. But elementary beddings, at the beginning I mentioned that having a category K, somewhat I can change its presentation, how it's embedded to structures. And some questions are presentation dependent and some questions are presentation independent. For instance, to the elementary bedding, it depends on language, on presentation. But lambda pure, it doesn't. Lambda pure can be defined just in terms of category itself. Well, omega pure, it means pure. This is known from group theory. So this is elementary with respect to positive primitive formulas. So this is something which is weaker than elementary. But it can be defined categorically. Well, just if you are curious, so I can just give definition. So this F is lambda pure if in any such combinatorial diagrams where these two objects are lambda presentables, then there is always morphism such that the left triangle commutes. This is definition of lambda pure. And somewhat one can view here, because if you take this object and you take its atomic diagram, so you have some positive primitive formula, which is true here, it should be true here. So in some sense, it causes the fact that it's elementary respect to positive primitive formulas in infinitary logic. But let's just define the terms of the category. So we don't need the powerful image, but only lambda pure powerful image. Just if you take bigger lambda, so of course you have less lambda pure things. So this lambda pure is a descending chain, and its intersection are split monomorphisms. It's a monomorphisms which are retractions. So this theorem is not true for split, but it's true for lambda pure, for any lambda. And the reason somewhat why we look at that is, and independently, in fact, it was also proved by Bonney and Unger, that any powerful image or accessible functor is accessible if and only if there's a proper class of almost only compact cardinals. So they realize the same weakening, but on the other hand, they show that it's equivalent to that. That's something is very important, because you see this, for instance, this question whether Freeman groups are accessible. It's theoretical because it sits between constructivity and large cardinals. But now this statement that any powerful image, and in fact any undoubtedly powerful image of topology accessible, is equivalent to the fact that it's a proper class of almost only compact cardinals. And the reason why this is interesting is that, you see, it appeared, so when I started to mention this abstract model theory, so in fact Shellac introduced abstract elementary classes as some classes of structures which are not defined by axioms, but that, I mean, for instance, usually you have a theory, you take all models which satisfy this theory, and you take homomorphism or invariance or elementary bendings or what you want. But here just subcategory of structures, and you put some condition on that. Part of this condition in fact says that this category is accessible, it's closed under identical limits. And one of the important conditions is that it's isofull, which I mentioned at the beginning, that any isomorphism between chosen structure is chosen. And tameness is a condition because here you can define types, but since you don't have formulas, you cannot define types using formulas. Instead, you define so-called Galois types, which they are called Galois because they correspond to orbit of monster model. And tameness is important smallness conditions, which in some sense says that that's some cardinal, that you have two types which are distinct on small domains, so they are distinct. And why it's important is that Grossberg van Dieren proved that under tameness, the Shellac categoristic conjecture, which is the famous conjecture, is true for successor cardinals. It means in the tame case, whenever you have successor cardinal which is sufficiently big, and your absolute class is categorical there, it means that the only object of that size is, there's only one object of that size. So then it's true starting from that time on. So it cannot happen that you have infinitely many or proper class for many jumps from categorical, non-categorical, categorical, non-categorical. Which in fact shows that a part of this conjecture somewhat depends on large cardinals. Having a proper class on three compact cardinals, so then this is true. And in some sense, this categorical conjecture somewhat could smell some set theory there because it changes proper class often. So this is why these powerful images appeared. And Bonney proved that using ultra filters, but then we showed this Mike Lieberman that it can be derived from this Mackay-Paré theorem. So now I want to show you another somewhat situation when some set theory appears. Let's say that locally presentable means to be accessible and co-complete. So all colimits. For instance, groups, Abelian groups are locally presentable because you have all colimits here. So these are very nice categories. So I am not going to give definitions here. Any definition what's a local stable model category. But model category is that's a way how to do homotopy theory, which was introduced by Quillen, that you have some ingredients and then you can make homotopy category of your category. And stable, it means that this homotopy category is special, in fact is triangulated. And a typical example of such thing is that you take derived category of a ring. You have a ring, you take complexes of the ring, then you have homotopy category, and then this is stable, and then you get triangulated category, which is derived category of a ring. But what's interesting is that if you take not simple sets that are not stable, if you take spectra, which is totally non-additive spectra, But then this stable category, this homotopy category, is in fact additive. Because any triangle is additive. Usually this category, of course, is not concrete, so you go to quotients of concrete categories. And this category is not nice in that sense that you have products of or coproducts, but you cannot expect to have equalizers or co-equalizers. They are replaced by fibers and cofibers. So now in some sense, this abstract model theory even goes to quotients of categories, and the result is that if you have locally measurable stable model category, so under Wopinka's principle, any full subcategory homotopy category which is closed under products and fibers, this is replacement of the fact to be closed under limits. So products are limits, you don't have equalizers, you have fibers instead, so product and fibers is just to be closed under limits. So it's reflective. I will explain the other thing in a moment, yes. And this was open problem, for instance, for spectra. The standard, say, stable model category. And it was open whether any, they call such categories localizing, so when any localizing category is reflective, or colocalizing, so it's reflective. So it's true under Wopinka's principle. And also, this is, I wanted to avoid too many definitions, but also if you take its left orthogonal thing, so it's co-reflective again. So this is something like that, anything close under co-limits is co-reflective. So you have the trace of that, in fact, in homotopy world, but here we don't know whether it's equivalent to Wopinka's principle. Yes, I am quite sure that it's theoretical, but we are not able to show this. Because usually how one tries to do such things is that, for instance, one embeds something when such bad things can happen, and you embed it to this stable homotopy category, which can be done, Abelian groups can be embedded here. But then you should close it under something which is called suspensions. If you have chain complex of suspensions, is that you go one stage up. And this is always present here. And those suspensions enlarge this category so that you lose control over everything. So we are not able to show that it's theoretical. So this is open for both questions. So that's open problem. So one of good properties of accessible category is they are closed under construction of limit type. Again, I'm not going to define what does it mean, but for instance, they are closed under products. Any product of accessible categories is accessible. One has to be a little bit careful with those construction of limit types, with those limits, because they should be taken in fact as limits among two categories. So one has not only objects, morphisms, natural transformations, and one has two instances of those, say, two limits. One is called inserter, which means that between two functors you insert morphism, natural transformation, or equifiers, that between two functors you have two natural transformations and you equify them. This is similar thing how you equalize a make equal to two morphisms. So this is just rough intuition what are considered limit type, but that's much more problematic for conception of co-limit type. And one result here, which I did with Beauparet, that accessible categories are closed in CAT. It means that these co-limits are calculated like among categories. And the related co-limits of accessible full embeddings, no set theory there. But if you go to embeddings, we could do it having a proper class of strongly compact cardinals. I give you one example. In fact, it's one open problem. So let's take such chain of accessible categories. So just set, then set 2, which means pairs of sets. Set n are n tuples of sets. And this functor, these functors f and n plus 1, always act, if you have n tuple you take n1 plus tuple by repeating the last instance. So what's the colimit? The colimit consists of sequences of sets which are eventually constant. And morphisms are also eventually constant sequences of mappings. So this is a direct colimit of embeddings, not full embeddings. These are not full as embeddings. So this category is accessible assuming the existence of an omega-1 stronic of a cardinal. But we don't know whether you need set theory for that, which is quite silly because it's very it's a natural construction. So maybe somebody with set theoretical background could do what we couldn't. So up to now I always talked about full subcategories, but now let's take something weaker. So let's take subcategories which are only isofull. Just to repeat it, so it means that if you have so maybe let's denote it in some way, for instance, as G. So now if you have two objects in your category and an isomorphism in structures, then in fact it is, so that's an isomorphism between your objects which goes to that one. This is a very natural condition because if you take somewhat any way how to construct subcategory, for instance, you take embeddings. Isomorphisms are embeddings. You take elementary embeddings. Isomorphisms are elementary embeddings. Or even if you take something like homotopy theory, for instance, cofibrations, so isomorphisms are cofibrations. So any reasonably definable thing is isofull. And I told you this isofullness eliminates this stupid thing that just to encode concrete category as subcategory of sets. So now we have only isofull subcategory, and still it's closer to limits and that is colimit. So it's reflective then. That was proved by Mackay and Pitts. And their proof was model theoretical. And just it's in fact now it's sketched here because they proved that the subcategory K is closed on the elementary submodels. And how they prove it? So one takes an object K in K, and one takes its elementary submodel. And one wants to show that it belongs to K as well. So at first, one saturates K by taking ultra power over a good ultrafilter. If you want to avoid GCH, so you have to iterate that. You have to take iterated ultra power, but I skipped it. So you take, and you know that this is saturated, and that is universally homogeneous. So it means that there are a lot of automorphisms. And they showed then this L here is equalizers of automorphisms here. And since this subcategory, so K belongs to K, this ultra power, any ultra power can be obtained as a directed colimit of powers. So since our category is closed under limits, under products, and that colimit is closed under ultra powers. So this ultra power also belongs to K. Since it's isofull, so all those automorphisms belong to K as well. And it's since closed under equalizer, so this L, which is equal to automorphism, so it belongs to K as well. So this is really model theoretical proof. And consequence of this is the fact that if it's full subcategory the limits and that colimit, so it's reflective. And in fact, what we did with Adamek, that for full subcategories we just eliminated this model theory, and instead of elementary embeddings we used pure embeddings. And we were absolutely happy with that proof, and we never looked at non-full subcategories, but somewhat it came again that these non-full subcategories are important. So we wanted to generalize this Mackay-Pitt thing from dynamic collimate to lambda-dilated collimates, like we did it with full subcategories. If you want to mimic this argument, so you also want to take this alter power, but since you don't have dynamic collimates but only kappa collimates, so this alter factor should be kappa complete. So, but one is ready to assume that kappa is compact, so that you have enough strongly compact cardinals. But unfortunately, there are some good alter filters also in this infinity context, but you cannot expect that this alter power is universally homogeneous. So you cannot do that. We had some correspondence with Sherlock about that, and for example, look at the well-ordered sets which you don't have any automorphisms there because it's auto-ordered rigid, only automorphism is identity. So you cannot expect that by taking omega 1 complete alter powers that you get a lot of automorphisms. So simply this method fails, and this problem is open. So whether it's true even at the sunset theory when you can go from full to isofull. So let me just to end with something quite recent, which is again a kind of appearances of these powerful images. Quite recently, Baldwin and Bonney put to archive a paper saying something about amalgamation properties and joint embedding properties. So joint embedding property means that having two objects, you can somewhat embed and joint to some other object. Amalgamation means that you can complete to a square, that you can amalgamate them. And the question was, so they did it with abstract elementary classes, so which are kind of accessible categories. And now you assume that you have this joint embedding property for objects which are small, which are kappa presentable in fact. And they prove that if there is a strongly compact cardinal, so then this general property in fact implies the full joint embedding property. And they did the proof using alter products again, but it can be done using these powerful images, and the trick is quite easy, because you take a category consisting of such configurations. So this is say L. And you go down by forgetting to your category K, in fact K square, having just those two candidates which you want to embed. And this function is accessible, and this image is powerful because whenever you can amalgamate that, so you can amalgamate in fact anything which, not only subobject, anything which goes here, because just you jointly embed it in that way. So it's powerful, this image. So having the cardinal, this image is accessible, but you assume that for any kappa presentable here, they can be amalgamated. But in fact, any pair is kappa collimates of those kappa small pairs. So this powerful image contains all pairs, which means that you have full joint embedding property. And the same trick can be used also with amalgamation property. So this is quite useful technology, this powerful image. And they also looked at something which is called disjoint amalgamation. It means that these two things are disjoint here. So disjoint amalgamation, which shows that this in this amalgam this a intersection of those. And you can do this as well by somewhat changing a little bit this category, assuming this disjoint is there, using some kind of limit sketches, and which is again accessible under sunset theory, and do the same thing. So that's all. Thank you.
Other questions?
Thanks very much for that. That was really interesting. So most of the examples you've given on the set theory side have all been either second order or first order schematic, which you expect with category theory. It's to do with classes of models being embedded into each other and so forth. So are there any category theoretic principles that are equivalent to just a single first order sentence with substantial strength?
Which kind of first order sentence you mean? Yes, for instance.
Just the so I mean, a natural example would be something like just there is a single measurable cardinal. So, but in terms of a kappa complete ultrafilter rather than focusing on the J.
Now, always in this result, which somewhat using large cardinals say something about some categories.
Yeah.
So you need this cardinal should be big enough.
Yeah.
So if, for instance, if like these three abelian groups, if everything is really down, so that's enough to have just one strongly compact cardinal.
Right. Okay.
So the fact that you need a proper class is that you want to handle all possible categories. Yeah. So if you, and that's I think related to this complexity thing in some sense also. Yes, that you can allow that having some easier situations. I don't know whether it's answered to your question or not.
Yeah, it's stuff to think about. Thanks.
Maybe I should mention also that the first order versus second order may not be the relevant distinction, because, for instance, to say there's a proper class of measurables, which sounds like second order, proper class.
Yeah.
It's equivalent to saying for every cardinal there's a
there's
measurable
one
above,
above,
and then
yeah,
it's
yeah,
first
yeah.
order.
Yeah.
So a lot of this is second order only for the sake of brevity.
Yeah.
Are there other questions, comments?
But it's an unbounded quantifier. I mean,
Yeah, exactly.
there are
That's
quantifiers
right,
which require unbounded
Yeah, well, and
quantification.
even one strongly compact
Yes, it's an
is
unbounded.
already unbounded. So yes, you need, the issue is how many quantifier alternations
I
of
think that
quantifiers
the-
and so on.
Sigma 2 statement in some sense.
Yeah.
So the issue is it's sigma 2 in the Levy hierarchy. So
Yeah.
sigma 2 is
Is the right,
right.
is what you want to do with first order.
Yeah.
Yes.
Yeah, you mentioned the Levy hierarchy earlier in the talk. I'm not familiar with that. What are the different classes of hierarchy?
Yes, somewhat you take appearances of unbounded quantifiers and how much you have to change for all and there exists. Yes, this thing, yes. Yes, I have to say that I had Joe, unfortunately, to tell me was the complexity because I was always making mistakes there. But it's quite nice exercise with some definition categorical to calculate its complexity in some sense. Yes, so but.
Okay, well, if there are no more questions, let's thank you.